Okay, so what is the answer of the first question? Anyone? Any team? Okay. What is your, which group are you? Group 2, okay, yeah. What is your answer? Say it again. Bet on only the first period, right? You want to bet on only the first period for the highest ROI, right? Is there any other answer other than this one? No, right? Everyone have the same answer. This is easy, right? Actually, simply just looking to the, right? But you you saw that, right? When you are looking for the best ROI, you always bet on the strategy that produce the highest probability, right? Isn't it, right? Because if you bet on the second one, it actually would like dilute, right? It would actually decrease the ratio of the return on investment, isn't it? Because the second one's ROI is actually lower than the first one, right? So if you do the average, it's kind of like pull down the average ROI, isn't it, right? So if you want to bet on ROI, then you have this one. Okay. So what is the answer of the second question? Anyone? Any team? Other than team 2. What is the answer of the second question? So what now, in order to answer this, you need to answer what is the strategy for the maximum expected return, right? The expected payoff, in other words. So what is the strategy that will produce the maximum expected payoff, net payoff? Yeah. Which one? Say it again. 9 bet, right? You bet to this point. Why do you say so? Right. It has actually among all is the highest cumulative payoff, right? If you do 10, you will like kind of like you can see that this cumulative payoff, net payoff increase, right? When you bet more and more, and then up to the increasement increase to the 9 bet, the 10th bet start to pull down the revenue, right? Okay, so if you want to have a strategy that looking for the maximum expected return, right? Okay. Yes.
Um, if the bets were a different amount, like say each bet was different, it wasn't all bets weren't $5. Would you still be able to do a list like this that show you the different?
Yes, you still be able to do it, but the simulation will be a little bit difficult. It was just a little change, right? Because if the number we only change this, right? Okay. If for some reason in each period you have a different cost, right? So the only thing that you need to change is to just change this.
So you would have to manually type each bet, or is there a way you could put it into like a vector or make it a?
Now you know the question, right? So we want to change the game rule so that the betting money is different from period to period, right? So first of all, you need to know the numbers, right? For example, from 1 minute to 2 minutes, it's like $5. From 2 minutes to 3 minutes, it's like $6. You need to have the rule, right? So as long as you have the rule, you can actually simply create a column here, right? the column is called cost, right? So instead of minus instead of doing this, right, number of bet times 5, you actually have to like,
It would be number of bets times like another a whole other column.
yeah, you need to do this
Cost.
things called cum sum, right? Cum sums means like cumulative sum. Okay. Let's try to do it. So you define a new column called cost, right? And the cumulative invest number would actually becomes cumulative sum of the cost. You get me? Of course, you need to start doing from here, right? Okay. The net payoff is no longer 100 times probability minus 5. It actually would become 100 times probability minus cost. You see my point? Right? Because right now it's no longer like every period at $5. It's like it changed, right? So if we change, we need to like define the column first. You get me? Okay. Then as long as you have that column, you just change this 5 into cost, right? And then here it's no longer number of bet times 5, right? It's actually cum sum of cost. That will solve the problem. You get me? Okay. Yeah. Okay. Any more question? Okay. No question. Now comes the difficult one. Okay. So you have by looking into the simulation, right? You see the strategy for maximum ROI and maximum payoff, but which of the two objective is better and why? Anyone have a question? Have a answer? Now this is tricky, right? It's actually no fixed answer, right? So any answer could be a good answer. But what is your opinion? If you want to make a choice, if you are the boss, right? If you are the manager who need to make a decision, how can you make a decision? And what is your decision? Yeah.
I think it depends how much money you have.
It really depends on what?
How much money you have to bet.
Depends on how much money, how many capital you have, right? If you do not have enough of time, enough of money, you might not want to do that, right? Isn't it? So according to what you say, it actually has a constraint on the seed investment, right? Okay. For example, you only have like $20. Okay. Then you might only want to bet on the thing, right? So in some case you have like $100 on your hand, right? Do you want to bet all of the 100? No. Why? Because starting from this one, the net payoff is negative, right? So a constraint is mean that you might not be bounded to the constraint, right? Sometimes it bound, sometimes it would not, right? Okay, that is a good one. That is a good one. Anyone has another consideration that might change your strategy?
I think it also depends on how many customers or how many people you're getting to play, because the number of bets is like a different column. So if you don't have that many people that want to play or that many customers, then I think the ROI, maximal ROI would be the best, because it only requires one bet, so you can keep doing that. But if you don't have 10 customers, like if you get 10 customers in 1 week, then it might not make sense to do the 9th or the 10th bet.
Yeah, you understand what what? Sorry, what is your name?
Nick.
Net.
Nick.
Nick.
Yes.
Nick. Okay. You understand what he say, right? It's also a reasonable strategy, right? So, and anyone else? So this is the difficulty of being a manager, right? Okay. The you have business objective, and that objective might not consistent with each other, right? So if we try to make a plot, okay, this is the number of ROI. This is the expected ROI, and this is the expected payoff. Okay, and the point is actually a strategy, right? This is 1 bet, 2 bet, 3 bet, right? So as you can see that the highest payoff is actually, because payoff is in the y-axis, right? So the highest payoff is at like 9, right? But the highest ROI is 1, right? Okay. So an easier way to help you make the decision is try to plot the strategy into what we call strategy space. Okay. Now in this strategy space, every point is an alternative strategy. Okay. You can bet up 1, 2, 3, 4, 5, and usually you will place the performance index as a dimension in the space. You get my point, right? So to help you make the decision, right, you can try to plot your simulation, right, into a chart, right, and we usually call it strategy space. So in this space, every point, every marker is an alternative strategy. Okay? And every dimension is one of the business objectives that you're looking for. Right? So payoff is something that we like. ROI is the other thing that we like. Right? But as you can see that here in this space, okay, there's a trade-off, right? From 9 to 1, okay? If you go in this direction, you will have a higher net payoff. If you go in this direction, you will have a higher ROI. Isn't it? Right? So these two things, these two performance index, we both of them we all want to do a maximization, right? But there's a trade-off between them. And that is a business decision that you need to make. Okay? So usually this decision is not made by data analyst. Okay? This decision is made by your boss, right? And it is your job to show this chart to your boss, right? So your boss can make decision easily. Isn't it? Right? Okay? So if you try to ask your boss, right, which strategy is more important, okay? Let me tell you, your boss would always tell you that both index are important, okay? As a manager, I think I told you, right, before I go back to school, I have played the roles of manager for like 20 years already, right? Okay. So every boss that I met would always tell me that all of these index are important, right? He would never give you one single objective that he want to maximize, right? Okay. So, and he want you to give him a strategic analysis, right? So what you need to do is something like this, right? You put all of the possible strategy on the chart, right? And show him the trade-off, or her, right? the trade-off between or amongst different objectives, isn't it? Right? So looking at this, she or he will have his own decision, right? He know the trade-off here, right? So he might want to know that, he might want to know that, okay? So he finally he might want to like choose 7 or 8 or 6 whatsoever, okay? And sometimes the strategy is also constrained by capital, right? By the number of customer, right? You might also have some constraint. So we make some strategy invalid, isn't it? Right? Okay. But the last thing that I want to show you, and also very important thing, is actually on this strategic space, some strategy are not reasonable. Okay. This strategy is actually reasonable, right? Because they are the trade-off of two objective, right? From 1 to 9. This 9 strategy, they are reasonable, all reasonable, right? It just depends on which the weight you want to place on the different strategy. But the strategy from 9 to 20 is not reasonable. Why are they? Why did I say so? Why are they not reasonable? Actually, in the space, you can see that this 1 to 9, this strategy are reasonable. They are so-called Pareto optimum. Did you learned this term before? Pareto optimum. So can you explain what is Pareto optimum?
It's like you got the positive payoff. It's like the magical, the base number that you get the positive accumulate payoff.
Do you understand what you say? It's difficult to explain, right? Easier to put. If you have the dimension as your objective, right? Okay. The point that have something on their upper right. If there's a point on its upper right, right? Then the point is unreasonable. Okay. For example, this point, right? It do not have anything on its upper right, right? This point do not have anything on its upper right. Okay. But this thing is not optimal. It is not Pareto optimal. Why? Because this thing is in its upper right, right? And this is not, because there are something on their upper right, right? So, well, if you have a point on your upper right, it means that there's a strategy that better than you in every dimension, right? So if you, it's no longer a trade-off, right? If you have a point, if you have a strategy that better than you in every objective, right? Then you should not choose the first one, right? You should go to that one, right? That's why we say that if you see something on its upper right, it's not Pareto optimum. And that is actually an easier way to explain what is Pareto optimum. Okay. Pareto optimum is the point that you cannot find anything that is superior than you in every dimension, right? Okay. If you cannot find a point that is better than you in every dimension, then you are Pareto optimum already. So in this definition, all of these points are Pareto optimum, and they are reasonable, right? And among this reasonable strategy, there's a trade-off, right? And there might be some constraint that further limit the validity of this reasonable strategy. You get my point? Okay. So in this exercise, what have we learned? Okay, we learn how to use model to do prediction, how to use prediction to do simulation, right? And how to use visualization to present the result of your simulation, right? Then after you do that, you actually have a very good presentation of the data, right? You actually have a very good strategic planning tool, right? That you can show to your boss, okay? And help him do the decision easily, isn't it? Right? Okay? Trust me, no boss would tell you which dimension is more important than the other. He would always tell you that every objective is important. Okay? And as an analyst, you need to have the capability to do something like this, right? Okay, every dimension is important. And these are the reasonable strategies that we can use, right? Okay? And they are trade-off between the objectives. So what is your decision? Okay? You are not the one who do the decision. But you should, as an analyst, you are not the one to do the decision, right? But you need to do something to help the decision maker make their decision easier, right? And that is what business analysis is, okay? After business analysis, usually you will not come out with a best solution, okay? Usually you will come up with something like this, okay? A chart that would display all of the strategies that you can choose, okay? And the trade-off amongst the reasonable alternatives, right? That is good enough. And that is the best thing that we can do, okay? Any question up to this point? So this exercise is like very important, right? So in this APP, we actually walk through a scenario that from data to statistic to charting to model to prediction to simulation and also to strategy planning, right? Okay, this is the entire life cycle, right? This is the entire process of business analytics. Okay, and that is why we spend a semester trying to teach you, right? Okay, any question? No, right? Okay. So make use of it, right? This is very important. Whatever business case, well, I believe that you are in the business school, right? So from time to time, someone will give you a business case and give you some data and want you to do a strategic planning, right? If you want to do the strategic planning in a quantitative way, right? If you have the data, you want to do the strategic planning on a quantitative way, this is the way that you do it, okay? Okay? Oh, all right. So, up to this point, we have already seen the whole picture of business analytics, okay? This is the whole picture of business analytics. Now, let's get back to what is this thing? Where is the? Let's get back to our unit web page. Actually, the probability that I have told you is actually very easy, right? We actually take the eruption time. We take a sample and then we make a we make a model and then we make a decision, right? That is one way to use probability, but in the realms of business, there are many different way to build model and estimate probability. Okay, and mostly let's take a look at this. Well, if you traditionally, if you learn probability, right, you will start from this, right? You would start to flip coin, right, and roll a dice, and then they will have some theoretical distributions, right? Normal distribution, Poisson distribution, binomial distribution, right? Geographic distribution, hypergeographic distribution. You learn a lot of theoretical distributions before you see the real things, right? Okay. They are, and this theoretical, the name that I just read, like binomial, like Poisson, like hypergeometrics, like normal distribution, like chi-square, like f, like t, whatever. That distribution are actually theoretical distributions, isn't it? That they actually does not come from data, right? This type of thing, they do not come from data, right? They come from assumption plus mathematics, right? So they are the most. They are some. There are some mathematicians, right? They derived from the assumption, right? They derived the theoretical distributions for us, okay? The way that we have done in the Old Festival case, in the case that we have just done, is things like this, right? We do the experiment or we do an observation, right? And we take the observation and do an empirical distribution, right? Okay. So sometimes you will go this way and sometimes you will go this way, okay? You have different approach, right? But whether you go this way or this way, you can always use program to do simulation, right? And that simulation will actually help you to make decision better, okay? So usually this way of doing mathematics will be taught in the Professor Li Chenxian's course, okay? Right? In his course here, he told you a lot of these distributions and how to do that, right? Okay, and in my course, I'll try to like piggyback on this background and try to teach you how to use probability to make decision making, right? Because I cannot like teach you the detail of all of these mathematical things. We do not have enough time to do so. Okay, that is the thing. So today I would like to show you how we can operate the theoretical. First of all, how we can operate this theoretical distribution in R. Okay, and the second thing is that we need to know how we can use theoretical distribution in real case. Okay, that is the two things that I will try to do in today's class. Okay, so if you go to as you can see that we are still in unit 8, right? But I add a new notebook here. Okay, so if you go to the sorry, this should be unit 8. Okay, if you go to the material, there should be a. You will see one more zip file. Okay, so you need to like download this zip file, and in this zip file, we also have the 8 folder, right? So you just put it on the original one, right? On top of the original one, okay? So there are some extra material that I add in this week, okay? After doing that, in your folder, you will see something like this. In your folder, you will see something like this, okay? You will have 3 different notebook A, B, and C. Let me do that, it's easier for you, I think. So we have A, we have B, and we have C, right? So we are today we only have time to, I think we only have time to go through B and C, right? Let me open the notebook first. This is 08B. So, as I told you, the first thing that before we lift probability, there are 2 more things that I want to do, right? The first thing is actually operational functions for distributions, okay? So we already know what is distribution, right? We already know what is distribution. And the form of distribution depends on the type of variable, okay? Right? For discrete, then for every different value, we will see its probability, right? Okay? For discrete type of variable, its distribution would tell you that because they are discrete, so in their domain, this is what we say domain, right? The range that the variable would change, we call it domain, right? In its domain, it's discrete, so you have a fixed numbers of category, and on each category you will have a probability, right? Okay, so it's easy. And however, for continuous variable, you will need to use distribution function, density function, right? Okay, it's no longer, you can no longer see the probability of each specific value, because for each specific value there's no probability. Right? You need to have a range before you have a probability. Okay. So in that case, we will need to use probability function. Actually, probability function also have 2 different types, right? If they are discrete, then you will have some binomial, like hypergeometrics, like Poisson, right? Like the negative binomial. All of these are actually theoretical distribution, okay? Binomial distribution, Poisson distribution, right? Negative binomial distribution, okay? They are discrete, okay? And there are some continuous distribution, and the most common continuous distribution is normal distribution, okay? All right. So let's see. So in the R environment, almost every theoretical distribution that you can ever find, okay, you can find it in R, okay. So you actually have has a lot of built-in distribution functions, right, including all of this, okay. So whatever distribution that you see in your probability and statistics notebook, textbook, is here already, okay. So all of the distribution is already built in the R environment, right? The point is how to use it, right? You have so many different type of distribution, then you need a way to use them, right? You need a way to use them, okay? And actually in R there are 4 operations that in general apply to all of the distributions. Let me say it again. In R, there are 4 operational functions: the D function, the P functions, the Q function and the R function, okay, that generally apply to all of these distributions, okay. So you only need to learn four functions, okay, and that four function would apply to all of the distribution that you would ever encounter, okay. Get me? So let me explain how what is this four functions and do some exercise. Okay, that's the first thing that we want to do. So see, let me explain this a little bit more, right? So the function will be look like something like the function actually start with D, P, Q, or R, okay? And then after the first letter is followed by the name of the distribution, okay? For example, for normal distribution, it would be D normal, P normal, Q norm, and also R norm. See that? Okay. For normal distribution, it's NORM, okay? And you actually put the first letter in front of the norm, and then there is a function called D norm, P norm, Q norm, and R norm, right? And for binomial distribution, it's called binom. Okay, this is binomial. Okay, so you have D binom, P binom, Q binom, R binom. Okay, for Poisson is boys. Okay, so you have P boys, Q boys, R boys, and D boys. See me? Okay, this is the way that we use the four operation function on different kind of distribution. Okay. Now, if you learn statistics and probability, you will learn that actually all of this, every distribution, every theoretical distribution, actually come with a form, right? For example, the normal distribution is a bell-shaped form, right? But the bell-shaped form can have different mean, have different expected value, and have different standard deviation, right? In that way, we will say that normal distribution has two parameters, right? That form is a general mathematical form of normal distribution, but actually in that form there are two parameters specifying the expected value and standard deviation of the bell-shaped distribution. You get it, right? So in order to use the function, as I say here, this is the distribution name, right? And these are the arguments of that distribution. For example, for normal distribution, you will need to specify its mean and its standard deviation. Okay, and for binomial, there are also two parameters, which is the number of trial. Sometimes we call it size. Okay, and also the probability of success, isn't it? Right. So all of this theoretical distribution, they have a mathematical form, and within that mathematical form, there are parameters, right, to specifically have the distribution. Okay. So the syntax for us to use this the syntax that we use these four functions is kind of like use D, P, Q, and R, followed by the name of the distribution. Okay, and then within the function call, you need to also provide the parameters of that theoretical associated with that theoretical distribution. Okay. Now, so what is D, P, Q, and R stand for? Okay, D actually stand for probability density function. Okay, we know what is the probability density function, right? It's a functional form. Okay, so given a value, so this is the x is the value of the variable. Okay, PDF. So, for example, like this is the PDF of a normal distribution, right? So given x, I would know the value of its density functions, right? So D is to give the value of density function. Okay? So we are giving it x. The x is actually the value of that variable. Okay? And given the value of that variable, we want to know the associated value of its density function. See that? Okay, you don't have to remember it. Later on, I will use some real example, and then you will have a better idea about this. I know that this is too conceptual, too abstract, and it's not easy to understand, right? It's not easy to understand and remember. Even you have learned it many times, right? You have learned probability in junior high, in senior high, in university, in graduate school, right? I think up to this point of time, you have learned probability many times. Okay, but still this thing are very abstract and very conceptual. So don't worry too much, okay? Just stay with me, and I was after these things I will show you like some real examples, so you will have better feeling about that. As I say, the D function is actually it transforms the value of a variable into the associated density. Okay, in the PDF, right? So PDF is by itself a function that transforms the value of the variable into its density, right? Isn't it, right? So PDF is actually the D function is actually the PDF itself. Okay. Now we rarely use this D function. Okay. If we want to estimate probability, usually we will use the P function. Okay. D stands for density, right? So it is actually giving you the value of the density function. But density is not probability, right? The way that we want to use most of the time, what we are interested is actually the probability. Okay, so if we want to know the probability, it's the P function. Okay. So P function, the input is actually Q, right? What is Q? Q is actually the boundary value. Okay, the boundary value. For example, if I do let me turn this way. See, this is PDF, right? And this is CDF. Okay, so if I say that if I give a CDF x1, it means the probability that x is below x1. Okay, CDF x1 is the probability that x is equal or less than x1. Okay, and CDF x2 is actually the probability that x is lower than x2. You get my point? Okay? So actually the CDF is the integration of the PDF from the left tail. Okay? Let me say it again, right? I know I can say it many, many times, and still you cannot remember it, okay? So, but let me try it one last time, okay? So, CDF x2, it means the probability that x is less than x2, okay? And CDF x1 is the probability that x is less than x1, okay? So mathematically, a CDF is actually just the integration of PDF from the left tail, okay? So if we want to calculate the probability of that x is between x1 and x2, okay? Just like what we have done in the old fast4 case, right? You actually use CDF x2 minus CDF x1. This is easier, right? Instead of doing integration on the PDF, right? Usually the mathematical form of the theoretical distribution are very complicated, right? So it's even more complicated when you do integration on it, okay? So it's very difficult to estimate probability in this way, right? So usually we will use the cumulative probability function, which in R it is written in this P function, okay? So P is actually CDF. Simply put, it is actually calculating the probability that the variable is less than Q, okay? It's CDF, right? So given a value, this function will return the probability that the variable is less than Q, okay? You get me? Okay. And this is more useful than the D function, right? Because actually, the only way to use the D function is just to plot, just to make the plot, okay? If you want to really calculate the probability, usually you will use the C function. It's easier, right? It's easy. Now, and then the third function is called Q function. The Q is actually this Q, okay? Right? Sometimes we would want to know that given. Sometimes we want to know that given an x, we want to know its cumulative density. Okay, we want to know its probability, and sometimes we know the probability, and we want to find the x. Okay. Sometimes we want to answer the question like, if I want to find the x, that the probability less than how do I say that? I want to, given the probability, for example, 0.2, right? So given the probability, I want to know the x, okay? So it's actually the reverse function of the CDF. Right? Sometimes we want to know this critical value, right, of given probability, okay? So let me finish this, right, before the break. So this function is that we given a value, given the critical value, we want to know the probability. And this thing is just reverse, okay? So given the probability, I want to know the critical value. Okay, so it's the reverse function of CDF. Okay. Sometimes you want to like, given the probability, you want to know the value. Okay. I want to know the boundary value. That probability is lower than 0.5. Okay. In that case, you will need to use the reverse CTF, right? Okay. And this R function is actually easy, right? It actually do random sampling, okay? It draw n point randomly from the distribution with this argument, okay? So this is the random draw function, okay? You will draw a sample of n point out of the distribution, okay? So depends on the n, it will return a vector. If the n is like 1,000, it will give you like 1,000 data point after the random draw, okay? So this four function, this is density function, which is the density function itself. And this is the probability function, which is the CDF, okay? And then this function, we call it quantile function, because given the probability, we want to know the critical value associated with this value, with this critical value. Okay, and then R for random sampling. Okay. Okay, I know that it's very difficult to like remember it at the first time, but don't worry. In the next hour, I will show you some real example. And if time is allowed, I'll also give you some real business case that we can use this function to do business decision. Okay. Okay, let's take a break and let's be back in. Let's take a short break. Okay, in 10 after 11.